Hi, WykD here. As the subject of multiple suspension points comes up time and time again, I thought I'd put out some information on the subject in an accessible form. I'm going to present data rather than advise you on what you shouldn't or should not do, and how you use this information is of course up to you to use in a responsible manner. What I will say is that while I don't use multiple suspension points in this manner as a regular thing, I have used multiple suspension points on occasions when I have, for instance, needed a suspension point between available load-bearing points, as there isn't one directly above the place where I want to suspend. On these occasions, I have done it armed with the knowledge of the effect of angle on load, and consequently used load-rated gear with a big margin of safety. On the screen now, you can see an illustration of load changing with angle. What you might notice is that the load does not go up very fast until you get above 90 degrees, at which point it starts to go up very fast. If we plot the angle against generated force, you can see how the forces go up slowly at first and then rocket off towards infinity. I have only illustrated up to 170 degrees, as it's very unlikely you would in any practical situations be able to get much closer to 180 degrees than this, and it's really unlikely that you'll even get as far as 170. For the sake of illustration, and to demonstrate why you don't want to get into a very high angle, I have calculated the force generated for a load of 100 kilograms at 179.99 degrees, which comes out at 572,957.8 kilograms, which is a lot in anybody's terms, and a very long way from the 573.69 kilograms, which we had only 9 degrees lower at 170 degrees. It should be obvious that this is a very dangerous amount of force. To show you how fast force goes up with only a small change of angle, we'll look at the force at 179.9 degrees versus 179.99 degrees, a change of less than 1/10 of 1 degree, and we will get from 57,295.79 kilograms to 572,957.8 kilograms, a change of 515,662.01 kilograms for a 0.09 degree change. This is an extreme example, but it shows you that once you're into high angles, the forces start to tend towards the infinite. With a very small weight, you can therefore generate huge amounts of force. Just to reinforce how fast the force rises with extreme angles, and just for the fun of it, I calculated the force for 179.9999999999 degrees. The figure you're seeing on the screen now is 5,733,305,919,302,599 kilograms. You are never going to achieve this kind of force in the real world, as you would already have broken everything, even getting anywhere close to this. I'm including this example just to show you how powerful and indeed dangerous high angles can be. There are angles that are better than others. I want to talk first about problems that occur at the bottom end of the scale with angles under 30 degrees. It may at first glance seem that these are good angles, as there is a very low force multiplication and the load is shared equally. In fact, it looks as if it is simply twice as strong as using one anchor point. There is, however, a problem with small angles. That is, that a small sideways force can cause the load to shift between the points, loading and unloading them. Imagine a load swinging like a pendulum, transferring load on and off both points, even with a very, very small movement. This is because the angle between the points is not great enough to ensure the stability of the distribution of force, even against the smallest horizontal component of force. Generally, the 30 to 90 degree zone is considered to be the good zone. 90 to 120 degrees is a cautionary zone. Anything beyond 120 degrees generates more force than your original load, and though this is not necessarily a showstopper, it's important to understand the forces and how to work with them. So, if you were to use multiple points, the best angles would be between 30 and 90 degrees, though maybe between 40 and 60 degrees is an even better range. One of the things I'm not covering in this video is when the load is not hanging vertically from a point, which it isn't in most of these examples illustrated. Most of the time in bondage, your suspended person is going to hang vertically unless you're pushing them off axis. If you do push them off the vertical axis, the vector forces will be changed, but also the angle of the forces on the anchor points. This has a big effect and is a serious safety consideration. But anchor points are outside the scope of this video, so I'm not covering that here. All of the values you've seen shown in this video are obtained by calculation. For those of you who are interested, here is the formula used to calculate those values. I don't think I can complete this video, however, without mentioning the famous American death triangle, which can multiply forces in a really frightening way. If we go back to our first graph, and add to that calculations for the same load and angles, but with the American death triangle set up, you will see how much worse it makes things. So what is the American death triangle? Imagine that we have the same anchors, and instead of connecting two independent slings which meet at your suspension point, you put a sling through them all and your loading point, making a circuit through all 3 points. This means that you have not only all the ways to fail, you have also the worst case force multipliers. This is because the points aren't just anchors, they're actually acting like pulley points, and they now have 2 forces acting upon them. In the example of the equilateral triangle, the force generated at the anchor points is 60% greater than if you had used 2 independent slings. There is no circumstances under which using the American death triangle is a good idea. It is absolutely to be avoided, and I'm including it here so that you know what it is, so that it can be avoided. On the subject of calculation, there is a load calculator now available on my website, link in the description, which will enable you to calculate the forces for 2 hard points for any load within reason. You can also change it to calculating the load for the American death triangle so that you can see the difference between them. I hope this is useful and the load calculator will be useful to you in future, and thank you for watching. Cheers.